In many situations, an electrical engineer or a designer will not get the capacitor with the exact capacitance that he's looking for. He may have other capacitors around, and he may have to combine them such a way that you get the effective capacitance that he's looking for his own design. In some other situations also, you'll be presented with a whole design, and because it's very, very complex, you may have to break them into blocks and analyze the blocks. If you have a block of a complex circuitry, then you may want to analyze and calculate the effective capacitance for a given block. Then you understand the other features or the other blocks better, or what the designer was trying to do. Today's lesson is going to help us be familiar with some of these ways of handling electrical circuits involving capacitors. As we go through today's lesson, try to achieve as much as possible the following objectives. Okay, so capacitor combination. What will be the effective capacitance when a number of capacitors are arranged either in series or in parallel? We start with series connection of capacitors and their effective capacitance. We have about 3. We are limiting ourselves to 3 for simplicity and clarity. We have 3 capacitors. They are arranged in series. What do we mean by series connection? So we can trace only one path through series components to the power source. If we have this power source, then we can say these components are in series if there is only a single path that we can trace to the source. If we take this path, we go through this one, we will go through this capacitor, we won't come back to it again, we go through this capacitor. From this one also, we go through this one before it ends up with a power source. Then we can say these capacitors are in series. You will see how it differs from the parallel connection shortly. We are calling the capacitance of the first one C1, the capacitance of the second one C2, and so on. We can add more. Then the power source has a potential difference or a voltage of V. So this V from the source, which is the energy per unit charge, will be shared among the 3 capacitors. The first capacitor will have a portion of it which we are calling V1. The second capacitor will have another portion which we are calling V2. Then the last portion will go to the 3rd capacitor. If we connect these capacitors and the high potential end of the battery is connected to the left side of the first capacitor, then electrons will be drawn from it, leaving some charges, positively charged plates here. That will induce equal amount of negative charges on the other plates. The equal amount of negative charges here will then induce positive charges on the other plates. I mean, if we've pulled 2 electrons from here, then this one will have 2 positive, which will also induce another negative charge here. If we have 2 charges here, positive charges here, to induce 2 negative charges here. These 2 negative charges would have been pulled from the other plate here, and this one will be positive. This one will induce the last set of negative charges, which will be pulled from the negative terminal of the battery. So what we are trying to say is that the quantity of charge on each capacitor plate that are connected in series are the same. If we have 2 millicoulombs here, then it will be 2 millicoulombs on the other plate and 2 millicoulombs. So the charges on each capacitor are the same. They are the same amount of charges that has been induced for series connection of capacitors. Okay, so we have the voltage being shared among all the 3 capacitors. But we know from definition, we got to know this equation from the last lecture, that the quantity of charge depends on the voltage applied, or the voltage across the capacitor, and the ratio between the charge and the voltage across it gives us the capacitance. We can rearrange this to get V equals Q over C. We are going to replace each of these voltages with their corresponding charge over C. So for the first one, we are talking about the amount of charge that has been drawn from the capacitor, and that will be Q, divided by the effective capacitance that we are looking for. This will be the effective capacitance that we are looking for. In other words, we are going to replace this whole arrangement with a single capacitor that has a capacitance of C. That will be equal to the charge on this one divided by its capacitance. So that is V1. V1 is equal to the charge on it divided by its capacitance C1. Then the voltage across the capacitor 2 will also be equal to the charge on it divided by its capacitance. Likewise, the third one, the voltage across the third capacitor will be equal to the charge on it divided by its capacitance. So all along we have the charge being equal. What it means is that if we should replace this whole thing with a single capacitor, that single capacitor will also have a charge of Q. This is it. That single capacitor will also have a charge of Q, the same as the smaller capacitors that were there before. We can simplify this equation by dividing through by the quantity of charge, and if we do so, we are going to have this simple equation that can be applied to any number of capacitors in series. So if we have capacitors in series, then we can add their inverses in order to get the inverse of the effective capacitance that can replace this system of capacitors. Alright, so we are going to talk for capacitors in parallel, and we need to understand what is meant by parallel connection. So here we have the source. This time we are bringing it here to save space. When we say the capacitors are in parallel arrangement, then what we are saying is that each component provides an alternative path to the source. That means if electrons are moving from the negative terminal, they can find alternative path to the source. If each component that provides alternative path to the source is a parallel connection. This is what I mean. If an electron leaves this side, it can decide to go through this one or that one. So these two capacitors are providing alternative path for the electron to go through. So they are in parallel. Alternatively, the electron can pass through here to the high potential end of the battery or the cell. So all these three capacitors are in parallel. That's what we mean by parallel connection. Some important features of parallel connection. Sum of the charges induced in each capacitor equals the total charge driven. So the cell here is driving a certain amount of charges, and the charges will be shared among the capacitors, unlike the series connection where the charges will be induced the same on each capacitor. This time around, the charges will be shared among the capacitors. So some of the charges will come to capacitor 1, some of the charges will come to capacitor 2, and in that order. I should have indicated the difference with the number of pluses here. Sorry for that. I think I will edit that later. The next point we need to keep in mind is that the potential difference PD across the capacitors are the same. So all these points are the same potential, and all these points are the same potential. They are the same potential as the battery, this end of the battery, which is 0. And this is the high potential end, the positive side. So all these points are the same potential. So if it is 1.5, then all these places will be at 1.5 volt potential, and all these places are at 0 potential. So the potential difference is 1.5 here, 1.5 here, and 1.5 here. It's the same throughout. Okay. Then, yeah, I think I need to illustrate what I mean by the same potential. What I mean by the same potential is, if an electron is moving from one potential point to the other, it doesn't matter which path it takes, the potential difference will remain the same. So an electron can start moving from B to A along this path, and it will have to lose 1.7 millijoules of energy. Another electron can also decide to move along this path. It appears this one is longer, and it is winding about. Another one can move around and then come to A. Whatever the case, they've all arrived at A, and they would have spent the same amount of energy. So it doesn't matter which path they take. Similarly, an electron from this side simply needs to get up here, and it doesn't matter which path it takes. It can go through this one or this one or that one. All that it needs is to come to this higher potential level. So if it goes through this one, it will lose the same amount of energy as going through this one or going through this one. Because they are in parallel connection, they provide alternative path for charges to move through. So the key point is that the potential difference across each capacitor is the same. The sum of the charges, if we should replace this one with a single capacitor, then that capacitor will have all the charges on it, and all those charges are currently shared among the 3 capacitors, Q1, Q2, Q3. Again, we are going to use the definition of capacitor, and we are going to replace each quantity of charge with its equivalent CV. So for the first Q, the effective capacitance will have with the voltage across it, which is V. We'll have this one here. Then for Q1, you are going to multiply its capacitance with the voltage across it. So C1 times V. Remember, the V's are the same across all the capacitors, so you are not going to give it any subscripts. So C1 V1 plus C2 multiplied by its V2. V is common to all the terms, so we divide through by V, and the equation is simplified. Very, very easy. What this one is telling us is that these 3 capacitors can be replaced with an equivalent capacitance C, and it will perform the same function as all the 3 doing together. So that is it for capacitors. You should be able to derive this expression as well as the one for the series connection. You should be able to derive it. It's one of the objectives for today's lecture. I think I will have a tutorial lecture and then help you appreciate how to handle some of these